Okay, so where the last video ended, we had found our equation for electric potential energy, which is a scalar, and it's measured in joules, and it's equal to KQQ over R. So if you look at our equations, our force is KQQ over R squared, our field is KQ over R squared, and now our energy is KQQ over R. So we have two Q's, two R's, 1Q, 2 R's, 2 Q's, 1 R, and now the equation we're developing is going to have 1 Q and 1 R. So we're going to have all the different combinations. The ones with R squared on the bottom are vectors. The ones with R on the just R on the bottom will be scalars. So what we were doing as the video ended was we were trying to come up with an equation that would allow us to find the electric potential energy at a spot without it being dependent upon the charge we brought in. So we're dividing that charge out. So what we're trying to find is often referred to as electric potential difference. Okay? Now, that's a long phrase, and physicists are sometimes a little slack and like to save marker ink and pen ink. And so once you get used to electric potential difference, you'll discover that they often just call it potential difference. And when you get used to potential difference, you'll discover they often just call it potential. And then there's also another name for it, which I'll tell you in a second. But first, let's go back to our units. So at the end of the video, we were saying, well, energy is measured in joules, and charge is measured in coulombs. So this electric potential difference is measured in joules per coulomb. And down here it would work out to be the same thing, right? K is Newton meters squared per coulomb squared times a coulomb over a meter. So 1 coulomb cancels, 1 meter cancels. So you'd have a Newton meter per coulomb, and a Newton meter is just a joule. Okay? But after people were working with this for a while, there was a guy that came along. His name was Alexander Volta, and he did a lot of work in this field. And so they decided to call this unit after him. And so a joule per coulomb is called a volt. And the other name for electric potential difference is voltage. So it's electric potential difference, potential, or voltage. They're all the same thing. But I couldn't put this side of the equation in until we got to that spot, because this side of the equation is a capital V. Okay, so we now have two equations for voltage, EQ over Q and KQ over R, which really match the two for fields, right? FQ over Q and KQ over R squared. So here are all our equations then. And they can be a little confusing because there's two capital E's, but the one with the subscript is energy and the one without the subscript is electric field. The ones with R squared on the bottom are vectors, and the ones with just R on the bottoms are scalars. And yeah, but the hardest part of this unit is figuring out which one refers to what. The energy one that you're going to do questions with tonight will be pretty straightforward, but I want to do some examples with the electric potential difference with voltage, because it's actually fairly straightforward. One of the things, though, you have to be careful of is that sometimes it will ask you for the potential difference at a point. Potential difference at a point. At is the key word there. They're asking you to find V, or even V total if there's a few other charges around. But if they ask you for the potential difference between two charges, so at a point, or at a point between, or between two charges. Okay, that's when you're going to do delta V, right? So this one, at a point, it wants you to add up all the voltages. But if it says between, then it's going to be delta V will equal the final minus the initial, okay? And these V's are voltages, not velocities. They're capitals. Okay, so I think in the notes I had posted for you, I gave you some examples, like the questions. I didn't give you the answers. So I don't know if you printed them out or not, but if you didn't, that's what we're going to look at right now. So example 1 says, calculate the electric potential difference at point A, located 10 centimeters from a charge of negative 20 microcoulombs. So here's my negative 20 microcoulombs, and 10 centimeters away at point A, we want to find the voltage. And so we're just going to do VA is equal to KQ over R. So 9 times 10 to the 9th Newton meters squared per coulomb squared times the negative 20 times 10 to the negative 6. And R is 0.1, and you don't need to square it this time. So the potential at A is negative 1.8 times 10 to the 6 volts. What does that mean? It means that the field would have done the work to get a positive test charge to this spot, because it's always a positive test charge that we use. So example 1, that's A. B says, calculate the electric potential difference at point B, located 5 centimeters away from the same charge. So point B is here, and we want to find VB. So it will be equal to KQB over R. Oh, sorry, it's not QB, it's just Q. It's that Q in the center. So 9 times 10 to the 9th Newton meters squared per coulomb squared. Remember, the Q on the top is the source. That should not have put that B in there. The Q is negative 20 to the negative 10, to the negative 6 coulombs. And this time it's halfway, it's 5 centimeters, so 0.05 of a meter. So VB will be equal to negative 3.6 times 10 to the 6 volts. Voltages are usually, when we're dealing with little charges, they're usually quite big. Part C says, what is the potential difference between them? Difference between them, meaning add them up. And it didn't say which one was first and which one was second, but I'm going to assume the first one they gave us was first, and the second one they gave us was second. So it's always final minus initial, so it'd be VB minus VA. So delta V would be negative 3.6 to the 6 volts minus a minus 1.8 to the 6 volts. Delta V is equal to negative 1.8 times 10 to the 6 volts. Again, negative meaning that a positive test charge would want to move from A to B. And so it says which point has higher potential, meaning remember, all of us will always move to the spot of lowest energy, spot of lowest potential energy or lowest energy. It's why when you get home, the first thing you do is lie on the couch or lying on the bed. You're going to the position that has the least energy in it. And so any positive test charge, any charge at all, when we release it, will always move to the point of lowest energy. And we're always doing it with a positive test charge. So if I put my little positive test charge here, where will it move? It will move to B. It will want to get closer. If I put it at B, it would never move to A if it's positive, okay? So that tells me that A has a higher potential and B has a lower potential. Okay, now I will end up doing example 2 in the next video, but just before that, if I had said what's the total voltage, well, I wouldn't. I'd need to have 2 charges. So in example 2, and I'm going to run out of time, but in example 2, we have 4 squares, 4 corners of a square, and 3 of them have charges on them, and it's asking you to find the potential at the other corner. In other words, find the V for each of these and add them up. Okay, we'll come back to it.